Socratic math tutor here. Today we're going to look at this function f, which it's defined in two parts, and so technically this is a hybrid function. And we're told that on the left-hand side of one, it takes this form, so this is a degree 1 polynomial, so basically a line. And on the right-hand side of one, it takes this very different form. Now the most important thing to notice here is that on the right-hand side, the only variable appearing is x, and so we know exactly what f looks like on the right-hand side of 1. Whereas on the left-hand side, we've got this m and this n here, and so although we know it has to be some kind of line, a priori we're actually not sure which one it is. Okay, so for part A, we're told, given that both f and its derivative are continuous over R, show that m has to be this particular number, -2, and n has to be this particular number, namely 4. So I just want to emphasize the direction we're trying to do here, where we're assuming f and f dash have this property, and then we're going to find what these numbers are, okay? And they're going to turn out to be these numbers. Now, what we're not allowed to do is go, okay, I know m has to be -2, I know n has to be 4, so let's take this data, let's plug it in here, let's work out exactly what f is, and then we'll just go ahead and confirm that it's continuous over R and that its derivative is too. So you're not allowed to do that, and the reason is because that's actually the backwards direction. So if we did that, we'd be proving that assuming this is true, it must follow that this line is true. And that's not what the question's asking. The question is actually asking the opposite direction. So what we need to do instead is assume that f and its derivative are continuous over R, and then we need to get these numbers popping out the end of our proof. And the fact that we're told these numbers here actually doesn't help us that much. I mean, it'll let us know if we've made a mistake. So if we get that m equals, I don't know, -3 or something like that, well, we probably made a mistake because they're saying that it has to be -2. But aside from that, being given these numbers actually doesn't help us that much. So these are just here in case you make a mistake, and I think that's worth understanding. Okay, so let's go ahead and use these two conditions to get constraints on these numbers we're trying to find. So what we can do is we can start by saying, since f is continuous, therefore, so the limit as x goes to 1 from the left-hand side of f of x has to be the limit as x goes to 1 from the right-hand side. So for this part, we're looking at the left-hand side of x equals 1, and therefore all we do is we just plug x equals 1 into here. And so basically we end up with m times 1 plus n on the left. On the right-hand side, we proceed similarly, so we just take this expression and we plug x equals 1 into here. And so we get 4 over 1 plus 1 squared. And so we can clean this up a little bit. Let's put m plus n here. On the right-hand side, we obviously have 4 over 2, which is just 2. And so this is our first constraint on these numbers we're trying to find. So for the next part, we're going to proceed as follows. Since f dash is defined on the entire real line, okay, how do we know that? Well, we're told that it's continuous over the entire real line. So obviously it has to be defined. So since f dash is defined on R, therefore, and we'll go ahead and just compute what f dash is. And so we just need to differentiate this in order to find each part of the function. So we've got a degree 1 polynomial here. We differentiate it, we lose the constant term. We just pick up an m here, and that's for x less than 1. And for the right-hand side, obviously we know it's going to be for x at least 1. And the question is really just how do we actually differentiate this? Okay, so there's a couple of ways of doing this. One of them involves the chain rule. The other approach, you could use the quotient rule. Personally, I prefer the chain rule. It's a little bit simpler and it's a little bit more fundamental. So, all right, d dx of 4 times 1 plus x squared to the -1. To differentiate this, we drop the power down, so we get -4 out the front. We rewrite this. The power reduces by 1, so we end up with a -2 here. And then we just have to multiply by the derivative of everything in the brackets, which is 2x. And obviously this simplifies to -8x over 1 plus x squared squared. Okay, so let's grab this. We'll put it into here. As you can probably see, I don't have quite enough space, but thankfully, due to the wonders of modern technology, I can make that bigger, can move that over a little bit. You know, Bob's your uncle, and there it is. So that's the derivative of f that we just worked out. Now I am running out of space a little bit, so once again, we'll use the wonders of modern technology. Put that up a little bit higher. You know, if you're following along with pen and paper, feel free to be just a little bit jealous of my magical powers here. We complain about technology all day, or at least I certainly complain about technology all day. But the reality is, it's pretty magical, you know, what it can do. So that was pretty convenient. And so we'll continue here. So since f dash is continuous, we could say continuous on R to be more specific. Now I'm just going to say continuous. That's probably clear enough. Therefore, the limit as x goes to 1 from the left-hand side of f dash of x has to be the limit as x goes to 1 from the right-hand side. Cool, and so what we want to do is basically, we're just going to go up here, and I'm going to stick x equals 1 into these formulae, which isn't very hard. So on the left-hand side, we get m. On the right-hand side, we get negative 8 times 1 over 1 plus 1 squared. And so obviously, okay, in the numerator, we have negative 8. In the denominator, we've got 4. And so that means m is negative 2. And that's really good news. That's exactly what we wanted to see, because lo and behold, m was supposed to be negative 2. And so we can use this to just check our working. Like I said at the start, these numbers are really just there for us to check our working, and that's exactly what we've done there. And, you know, getting the other number is obviously pretty easy at this point. We've got this equation. You know, let's go ahead and just call this something. So let's call this a. So then we can come down here and we can say, therefore, using a, we have, and I'll just copy out a again, but with m replaced with the value that we just found. So we're going to get negative 2 plus n equals 2, and therefore n equals 4. Once again, we got the exact value that we needed, and so that lets us know that we're done with part A. Okay, so let's go to part B. The task is to find the area enclosed by the following. So there's the graph of the function, there's the x-axis, and there's two more lines, x equals 0 and x equals root 3. So to actually understand what they're asking here, I think it's helpful to just draw a quick little sketch, label our axes. Okay, so here's the line x equals 0. Here's the line x equals root 3. Somewhere in between them, we've got this special number 1, where our graph changes shape. And so we know that on the left of 1, we've got this linear graph that's descending, and it's descending because m is negative 2, so we have a negative gradient. It's descending there, and then it starts looking like something else past here. Who really cares what it looks like? It's not that important. And so we've depicted the graph of the function. We've got these two lines. Now we just need to put in the x-axis, which is this bit. And so therefore, this part is what we're trying to find the area of. Okay, so let's go up here. Let's get rid of all this stuff. That was part A, so we don't need that anymore. Might as well get rid of these green bits as well. And basically what we're trying to do is we're trying to find the area, which is the integral from 0 to root 3 of f of x dx. Okay, and this breaks up into two integrals. So we have the integral from 0 to 1 of this part. And we know what m and n are, and that's really why they gave it to us, so that if we got stuck with this first question, it wouldn't be such a big deal. We could still do the second part. I think that's probably why they gave us the numbers. And so we'll just put those right in. So we have negative 2x plus 4 dx here. Might just put brackets here for clarity. Not strictly speaking necessary, but it just looks a bit more logical to my eyes. And then over here, we have the second integral. So it goes from 1 to root 3. We put 4 over 1 plus x squared in here. Now we could try and solve these separately, give each of them a name, call this one A, call this one B, something like that. But honestly, these integrals are easy enough that I feel like we almost don't need to go like quite to that level. And so what we'll do is we'll just work it out. We'll go, okay, the integral of 2x is obviously x squared, so negative x squared here, put a plus 4x here. We're integrating from 0 to 1. That's the first integral. As for the second, we'll pull out the 4. We're going to end up with 1 over 1 plus x squared in here, and the integral of that is arctan. We actually saw that in the previous question. Get our terminals going. So now we'll just put our numbers in. We'll set x equals to 1. Get negative 1 squared plus 4 times 1. I'll just write plus 4. So that's our first bracket, right? Obviously, if we put x equals 0 in here, we're just going to get 0. So I won't even bother putting that in. And then for the second bit, we get plus 4 times arctan of root 3 minus arctan of 1. And just for clarity, I actually feel like it's best to put in some more brackets there, just so we don't get confused about the order in which the negative and the squaring take place, because that could definitely, that could throw us. Okay, so this equals negative 1 plus 4, which is 3, plus 4 times, now hopefully you know your special angles. So arctan of root 3, that's 60 degrees, or in other words, it's pi on 3. Arctan of 1 is 45 degrees, or in other words, pi on 4. And so this is 3 plus 4 times common denominators. We get a 4 pi here, 3 pi here. We're dividing by 12. We'll just simplify things a little bit. 4 over 12 is, it constitutes division by 3. 4 pi minus 3 pi is pi. And there's your answer. And so there you have it. So we found this area. It's the area enclosed by the graph of the function and these 3 lines. And we worked out that it's 3 plus pi over 3. And the nice thing about specialist math is that you're not expected to give any decimal approximations unless they're specifically asked for. So therefore, this is a final answer, and this should get you full marks for this question.